here we go. We're going to write a Maclaurin series for sine x. Okay, we're not necessarily writing a Maclaurin polynomial that terminates with a set number of terms. We're writing a Maclaurin infinite series. So we're going to have an infinite number of terms, which really means we need to find the pattern and make sure we can solidify that pattern with a general term. Here's what I think we should do. Let's start by just finding lots and lots of derivatives. I'm going to go a little crazy on this one. I'm going to take it all the way at least to the 7th derivative. The pattern goes very quickly though, so let's just jump right in. So f of x is sine x, so f prime of x, I'm going to write as fast as I can. It's cosine f double prime, ooh, that's ugly. F double prime of x is negative sine x. F triple prime of x is negative cosine x, and then beautifully going back to where we started, the 4th derivative of any trig function is that original trig function. Takes me back to sine. Well, as long as it's not a chain rule issue. All right, let's keep going. You can see where this is going, but it's going to come in handy in the process of conversation. So there's that. F6, come back, come back. It'll come back now. There we go. Negative sine x. I was working so fast the computer couldn't keep up. Ha ha. F7 is negative cosine x. And then 8th derivative is going to give me sine x. Boom. There we go. All right. In the process of doing this, I don't know why I'm clapping my hands together like the little monkeys with the symbols. In the process of doing this, we're going to need to evaluate each of these, sounds like a lot, but it's not, where this polynomial is centered. Because it is a Maclaurin polynomial, is centered at 0, so we're going to evaluate all of these with green at 0. Quick process. Here we go. F of 0 is, well, 0. F prime of 0, cosine of 0 is 1. F double prime of 0 is 0. F triple prime of 0 is negative 1. 4th derivative is 0. You can see where this is going. Every other term is 0. It's neat the way this works. 5th is 1. 6th is 0. 7th is negative 1. 8th is 0. Okay, we now have some information that we can use to build our Maclaurin polynomial. Taylor polynomial centered at 0 is a Maclaurin polynomial. So we're going to build this polynomial, and when we build this polynomial, we're going to get a general idea of what the structure of this looks like, and we'll continue to kind of finagle that until we can get a general term. You'll know what I mean by that. Let me tell you what I mean by that now. The general term is not where I specifically have numbers in there. I mean, I'll have numbers in there, but it's going to have the variable n in there because I want to be able to get to any given term number by plugging in the appropriate n value. All right, so let's keep going. A Maclaurin polynomial is this, and I'm just going to start writing. I'm going to call it t of x because it's a Taylor polynomial centered at 0. I didn't want to call it m of x because I just didn't want to call it m of x. This is going to look very familiar. You've seen this. So this would be f of 0, the 0th derivative at 0 because it's a Maclaurin polynomial. X to the, I'll drop my marker there, x to the 0 over 0 factorial, a lot of unnecessariness in there, plus f prime of 0, x to the 1, that's a 1, not a derivative, 1 factorial. I need to clean this up just a little bit. That looks a little bit sloppy. There we go. That's x to the 1. I like to put understood exponents in here for the sake of the pattern. That's just how I roll. Plus f double prime of 0, x squared over 2 factorial, f triple prime of 0, x to the 3rd over 3 factorial, and so on. All right, it keeps going forever. So we are going to write enough terms to where we can start pattern sniffing. It's what I call it. It's awkward, but that's what we call it, what I call it. So we're going to sniff out a pattern and then hopefully keep going with this process. Now I know I went all the way to 8 here and I stopped here at 3, but we're going to keep going with it. You'll see what the process is. So when I find the value of the function at 0, I get 0, which makes this entire term 0 plus. Okay, f prime of 0 was 1. 1 x to the 1 over 1 factorial. 1x to the 1 over 1 factorial. Lots of unnecessariness. I like to keep it. It helps me sniff patterns. A scratch and sniff math book. That would be exciting. Find the pattern. Okay, f double prime of 0 was 0, so that term is 0. And then the term that has an x cubed is going to be negative 1. So negative 1 x to the third over 3 factorial. Now, let's continue with the patterns. Every odd exponent term is 0. So gone, gone. X to the fourth is gone. X to the fifth is going to stay. X to the sixth is gone. X to the seventh is going to stay. X to the 8 is gone. X to the 9 is going to stay. So let's keep writing just a little bit. And I have 1, I don't know why I'm putting the 1s, x to the 5th over 5 factorial, 0, and then we'll do one more, minus 1 x to the 7 over 7 factorial, and it keeps going. Plus forever and ever and ever. Okay, let's find some patterns. Sorry, I got right up in the camera there. Find some patterns and you're going to like it. First of all, let's drop some zeros out. So my zeros are going, and I'm going to have 1x to the first over 1 factorial. Again, I like to write unnecessariness. Minus 1x to the third over 3 factorial plus 1x to the fifth over 5 factorial minus 1x to the seventh over 7 factorial plus, and we keep going. Okay, so we used to, about 20 seconds ago, say this is term number 0, term number 1, term number 2, term number 3, but every other term was 0, so it just canceled out. Okay, so normally we would start this thing by saying, okay, I'd plug in 0 and get something, plug in 1 and get something, plug in 2 and get something, plug in 3. I don't want to do that because every other term is completely pointless, so we're going to get rid of them and we're going to renumber in a sense. So here's what's about to happen. If nothing I just said made sense, it's about to click. Let's use that color. And you had your heart set, like purple, yes, no. Okay, this is the zeroth term, if you want to count it like that. But basically, this is where n equals 0, and this is where n equals 1, and this is where n equals 2, and this is where n equals 3, and you can see it goes on forever, right? So in your head, on paper, somewhere, you can make a little chart, and I'm going to make a little chart. Slide this up for a second, make a chart, and then I'm just going to slide it back down, copy this or not. But here's what's happening. I am really trying to be able to write the next step. Let me rephrase that. I want to write a general term. Let's actually go ahead and start this idea. Let's start this process over here. My general term will be what I get if I plug in the term number 0, 1, 2, 3, 4, 5, whatever, and I'm able to crank out something, okay? So let's just start building a few things. First of all, I know it's going to be a fraction. Second of all, I know it's going to have an x. That x is going to have an exponent. And I know I'm going to have something down here that's a factorial. Okay, so we're going to have that. We're going to have this. There's an exponent. There's a factorial. And they're going to be the same thing. I'm noticing this, and I see 7, 7, 5, 5, 3, 3, 1, 1. Okay, they're the same. This is pattern sniffing. They are the same. I know I'm going to have a 1 here, but is that 1 going to be positive or negative? Don't know. I don't know. All right, so let's pause that idea. We're about to find the general term. Goes on beyond that, by the way. And then we will write it as a sum. So I'm going to pause right here. I know I've said a lot, and we're going to just start the whole thing over. Find all your derivatives, evaluate your derivatives, plug it in, And when you plug it in, you're going to be able to start finding some patterns. That pattern is going to help you get the general term. This right here is going to have n's in it, and that is going to help me say, okay, I can predict this term, this term, this term. And it's going to lead me to my final answer, which we'll get to in a few minutes. Okay, back to what I wrote when you were disappointed that I didn't write with purple. And back to the table that I mentioned earlier when I got sidetracked. If n was, let's go way up. That's far enough. If n was 0, then we'll just call it the exponent, was 1. Okay, you can do this in your head if you want. Again, head, scrap paper, whatever. When n was 1, my exponent was 3. When n was 2, my exponent was 5. And when n was 3, my exponent was 7. And if you want to go further, I mean, you can see where this is headed. 4 gives me 9. Okay, and we did some similar stuff on some notes called Notice the Pattern, something like that. It's this sheet where you had to like sniff patterns. It's fun. Scratch and sniff. So I want to find what I could do to this number to get this number. And immediately you notice that it's linear. So as I go up by 1 here, I'm going up by 2 here. So the slope of this idea right here, the slope of this is going to be 2. So for whatever n value I plug in, there it goes. For whatever n value I plug in, I know that my slope is going to be 2 of those. And then, right, that's inaccurate, clearly, because double the 2, you don't get 5. Double the 3, you don't get 7. But if I double it and then add 1, I will get what I want. Okay? So whatever term number I'm on, whether it's the 0th term or the 4th term or the 150th term or the nth term, take whatever term number you're on, double it and add 1, and that is going to be your exponent, which is also your denominator with the factorial on it. So let's switch colors again. We're going back over here. 2n plus 1 is my denominator with factorial, and then 2n plus 1 is my exponent. Okay, we haven't dealt with the fact that this thing is alternating. So we know we have a -1, and it has some exponent on it. And every exponent on it, well, the exponents on it are going to cause the sign to switch back and forth from positive to negative, positive, negative. Literally, positive to negative, positive to negative. So what I need to do is determine the exponent of this -1, not quite done here. I need to determine the exponent of that -1 so I can make sure that every even term, starting with 0, is going to be positive, and every odd term is going to be negative. Okay, a negative number to an even power gives me a positive, and that's what I want. I want the evens to be positive, so we'll just raise it to the n, mission accomplished. Okay, I say mission accomplished, we're going to write the final answer. So, back to the beginning. We'll start the whole thing over. No, I'm kidding. Sine is this. Notice that we're adding lots of stuff, starting with 0 and going forever. So my final answer, written in the purple that you've waited for, is this. Sine x equals the sum from 0 to infinity of this term. Because if I plug in 0, I get this term. Plug in 1, get this term. Plug in 2, plug in 3, plug in 4, plug forever, and this is what you get. Now there's some amazing things that I want to talk about on this. There we go. Although we are technically done with this problem, and this is something that you need to memorize, let's highlight it. This goes in your notes. There's a place for it in your notes. You need to memorize that. Here's one way that I memorize it. First of all, I know it's alternating. Second of all, here's a thing that I kind of latch onto in my memory. Sine is an odd function. We'll scroll up for a second. You don't have to write any of this if you don't want to. But sine is an odd function. odd functions are symmetric around the origin, meaning if you rotate it, it'll lay on top of itself. Let me try to draw the sine function as best as I can, roughly. That's sine function. So if I took this right here where my wrist is, and I bent it back around and rotated it 180 degrees, I would get the same graph. I didn't draw it perfectly, but about the same. It's about the same. So this, since sine, let's put the e on it this time, is an odd function, I know that all the exponents of sine are odd. Watch this. All the exponents of sine are odd. Okay, looking ahead, we're going to do cosine in a minute. Cosine's an even function. All of them are going to be even. One more thing. There are people, and I won't name names, but there are some mathematicians that jokingly say this. Are they right? No. Are they close? Yeah. And here's why. Sine x equals x for values of x close to 0. The line y equals x is, assuming I have a slope that's tilted just a little bit here, y equals x is that. It is the tangent line. The tangent line, oh, this is beautiful. The tangent line of sine, centered at 0, the first degree Taylor polynomial is x. If we found the tangent line of sine at 0, we would get the line y equals x. So x, just x, is a good approximation for sine for values close to 0. That's what tangent lines do. Notice that that is the first term. Beautiful, isn't it? You know you agree.